Hello, this is Ms. DB. Today we're going to do a short overview of quadratic functions. And we're not going to discuss all the details about quadratic functions and all the different things that we'll do with them. That's a whole chapter in itself, but that's just a quick overview. So the standard form of a quadratic function is f of x equals ax squared plus bx plus c. So you'll have a variable squared in a quadratic function, and a cannot be 0 because if it was you wouldn't have that term and it would be linear. Here's some of the properties of a parabola. A parabola is the graph that you get when you graph a quadratic function. So it will have an axis of symmetry. That means that you could fold it on that line and this side would land exactly on that side. So they would look exactly the same. You can also say that they're mirror images of each other about that line. And it will either open upward or downward. It opens upward if the a in front of the x squared is a positive number, and it'll open downward if that number is negative. You can also use the a, b, and c to find the exact equation for the axis of symmetry. It would be negative b over 2 times a. That will give you the exact equation. And the vertex is this point right here. The vertex is either the maximum or the minimum of your parabola, of your quadratic function, and it can be found using the x value of your axis of symmetry, because your axis of symmetry is going to be x equals some number. That's the x value of the vertex. And to find the y value, you just plug that number into the equation and see what you get. And the y-intercept is c. It's that number at the end there. And the y-intercept, remember, is where it crosses the y-axis. So if the parabola opens upward, which is when a is a positive number, you will have a minimum value like that. And that's the vertex. And when the parabola opens downward, when you have a negative a value, then your vertex will be the maximum. The domain of either of these is all real numbers. And the range depends on whether you have a minimum or a maximum. So if you have a minimum, if your parabola opens up, then your range will be y is greater than or equal to the y value of that minimum point of that vertex. And if you have a parabola that opens downward, then you'll have a maximum. Then the range will be y is less than or equal to the y value of that maximum point of that vertex. So you can graph functions in standard form by determining first if they open upward or downward. You can find the axis of symmetry. You can find the vertex by taking the x value of the axis of symmetry and then plugging it back into the equation and solving to find the y value of the vertex. You can find the x-intercept or the y-intercept because it's just the constant at the end of the equation. So this one would have a y-intercept of 6. Let's see, what else can we find here? And then you can put those points on your graph and draw a smooth curve that goes through your points. You can also, of course, graph these using technology like a graphing calculator or Desmos or Sketchpad. And then just make sure that you know what all of those points would be and how to find them. So on your worksheet, you're going to do that for a couple different parabolas, a couple different quadratic functions. So in 9 and 10 you're going to do that, and then you're going to answer some questions. Let's try number 10, I mean. So we have negative x squared plus 2x minus 1. So because it's a negative here, I know that this is going to open downward. And if it opens downward, then we've already used some words last week about properties of functions. That means it's concave down. It's going to be symmetric about the line, which is the axis of symmetry, and we can use a would be negative 1, b would be 2. We don't need c for this, but later on we'll need that c is negative 1. So we can plug those into this formula to find the equation of the axis of symmetry. So negative b would be negative 2 over 2 times a is negative 1. So this would be negative 2 over negative 2 is 1. So the axis of symmetry is x equals 1. I'm going to put that on here right now. Here's x equals 1. I'm just going to draw a dashed line to show that that's going to be my axis of symmetry. So the vertex will have 1 for the x value, and to find the y value of the vertex, I plug 1 into my function. So it would be negative 1 squared, because see, we have a negative and then 1 squared, plus 2 times 1 minus 1. So negative 1, 1 squared is 1, plus 2 minus 1. So negative 1 plus 2 is 1, minus 1 is 0. So the y value of my vertex is 0. So I have a vertex at 1, 0, so right here. And this vertex, because it's opening downward, this vertex will be the maximum point. And let's find the y-intercept. The y-intercept is at negative 1. So here's that. Now, I know it's symmetric about this dotted line, so I can put another point over here because they would have to line up. Let's find one more value. Let's see what, if I let x be 3, let's see what I get. So if I plug 3 into this equation, I would have negative 3 squared plus 2 times 3 minus 1. So that would be negative 9 plus 6 minus 1. Negative 9 plus 6 is negative 3 minus 1 would be negative 4. So there's a point at 3, negative 4. 1, 2, 3, 4. And there would also be a point over here that would be symmetric. So now I'm ready to draw my curve. I'm going to go through the points, close like that, and just put my arrows to show that this would continue in that direction. Okay, we can also factor this to find the x-intercepts, but I can see on this graph that the x-intercept is there's only one of them, and it's at 1. But we can do this to practice. I factored the negative 1 out to make this easier to factor. So factoring is when you put your two sets of parentheses, and I need the factors of 1 that will add up to negative 2. So 1 times 1 is 1, or negative 1 times negative 1 is also 1. So I want the negatives because I have to add them together to get negative 2. So that means that they're both the same factor. That means if I set this equal to 0, I will find my x-intercept, but I already knew that it was going to be 1. So my x-intercept is at x equals 1. The domain of all quadratic functions, unless there's some reason that it's not, would be all real numbers. And the range, this is a maximum point. So y will always be less than or equal to that point, and that point is 0. That y value of that point is 0. So we've answered all the questions, and I didn't have to graph it using technology because I was able to use all of these tools. However, you can graph with technology and then paste your graph here if you prefer to do that, or if you just want to check it. So we already talked a little bit about this, but the x-intercepts are also called the zeros of a function. So when you are asked to solve a quadratic equation, you are going to be looking for the x-intercepts. They often will have 2. In this last example, there was only 1 in the one that we graphed, but you can have 2, or sometimes you'll even have no x-intercepts. So you can have 1, like this number 10, or 2, like this example, or occasionally you won't have any real zeros. So we can find the zeros from a graph, or we can find using factoring, like we did in number 10. We factored and we looked at the graph. Or you can use a table, and if you find that you get the answer of 0, then you know that if f of x is equal to 0, then you know that that's a 0. So we had negative 3, 0, that's one of them, 1, 0 is another one. And here's another example with factoring, a little bit more complicated. We did some other methods too. We did completing the square, we did finding the zeros by taking the square root. Occasionally you can do that. And then if all else fails, you can use the quadratic formula. The quadratic formula is also how we did it when we looked for the non-real zeros, when we looked for imaginary or complex roots. We're not going to do that on this worksheet. On this worksheet, it says to solve the following quadratic equations. That means to find the zeros. So you could solve with graphing. If you do that, then please paste the graph on this page. Or you can solve by factoring, or you could use the quadratic formula, or you could try some other method. Now it says y equals. When we're looking for the zeros, we're going to replace y with 0 so that we can find the zeros. In this one, I would start by factoring out a -1, or I could just reorder this so that I would have 4 minus x squared. The reason I'm doing this is just to make it easier to not have a negative there. So I think this is a perfect square, right? So this I could write as 2 and 2, and I could try this as x, and 1 is a negative and 1 is a plus. And if I FOIL that back, I would get 2 times 2 is 4, plus 2x minus 2x would cancel. Negative x times negative x, or negative x times positive x is negative x squared. So I'm going to solve that for x, and I'm going to solve this for x. This one's easier. X is equal to -2, and on this one I would get negative x equals -2, or x equals 2. This one could have been solved with square roots too. If I have 0 equals -x squared plus 4, I could add x squared to both sides, and I'd have x squared equals 4. Take the square root of both sides. When you take the square root of a number, we often just say it's 2, but there's really 2 roots. There's the positive and the negative, because -2 squared would also equal 4. So there's your 2 answers as well. And number 12 is kind of similar, and these ones you can solve by factoring. In number 14, I would factor a -1 out. That'd be plus 10x plus 25. And then look for the factors of 25 that will add together to get 10. And then finally, there's a real-world problem of Philip is throwing a ball, and he's got this equation, and you're going to find out how long it takes the ball to come back to the ground, look at the x-intercepts or roots, and what's the maximum height, look at the y value of the vertex. This one might be a good one to graph. All right, thank you, and have a great day.